Hello, everyone. Welcome to the XCamp 2024-2025 season. December, actually, it's a January contest bronze level live solution. It's going to be led by the lecturer of XCamp, Alex Zhu. He is in USACO planning level, and he currently study computer science in UC Berkeley. And in the next hour, he's gonna walk through the January bronze level contest problems with everyone here. Feel free to discuss with him about strategy and also the problems as well. So at the very beginning, given some of you may not know XCamp that well, we'll play a short video.
Computer science and artificial intelligence are tools that will change the future. XCamp Academy is a community dedicated to inspiring and cultivating the next generation of computer science and artificial intelligence talent. XCamp Academy was founded in August 2017 in Silicon Valley by two Google software engineers. The name XCamp was inspired by the variable X, which represents unlimited opportunities. XCamp's curriculum system and training methodology is inherited from Mr. Xianyou Xu, a Chinese diamond-level international gold medal coach. Our staff here in the US is mostly composed of senior software engineers from tech companies in Silicon Valley and prestigious CS students from top universities. In addition, we have strong support from international and domestic competition winners in our coach team. From beginner-level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of mid-2024, more than 300 XCamp students have reached the USACO Silver Division and above, including 60 in the Platinum Division, and 27 were selected in the US and Canada national camps, out of which 15 were fresh in the 2024 season and 2 were selected for the US national team. In renowned high school contests, Stanford's Procol and UC Berkeley's Calico, and other prestigious US programming competitions, such as the Harvard Programming Invitational, Teams Code, and Lexington Informatics Tournament, XCamp students perform well, and we encourage students from being participants to problem writers and organizers. Our students received 13 MIT offers and many more from Stanford and UC Berkeley, thrilling us all. Here at XCamp, we believe that children have unlimited potential and can change the world through coding.
Okay. Yeah, and for some of you who doesn't know XCamp that well, XCamp is specialized in training students in USACO competition. It's short for USA Computing in Olympiad. And also, we also work on strengthening the STEM education for larger group of students as well. For the past several years, we've got more than 300 students got USACO silver level and above, and more than 60 in USACO platinum above, and 27 USACO or Canada national finalists, 2 EGOI medalists, and 1 IOI gold medalist, ranked the third in the world last September in Egypt. It's really good achievement, and we hope you can also walk through the same path and achieve your own success. And a little bit introduction is that in the following several months, XCamp is going to host different efforts to help you with your coding education, STEM education, and USACO education as well. We have the on-site summer camp this summer from July 21st to August 1st. And we have the camp for all levels, and is hosted in the Bay Area. You can choose from 5 days or 10 days. And we have year-round weekend class. It's 4 quarters per year, 10 weeks per quarter, and we will help you to build a solid knowledge foundation. We do have the USACO mock test class as well. It's kind of similar to the live solution, but it's just the proper problems are arranged and prepared by XCamp lecturers. And we do have a Grandmaster class. The the extremely strong competitive programming participants from the previous page, they got into the national camp and IOI medalist. They are all trained out of the Grandmaster class. If you have a very strong motivation to pass USACO Gold, do well in Platinum, and want to enter the camp or achieve the IOI gold medal, and then this is a class for you to go. And we also have the APCSA series as well. Okay, now I'll turn the stage, hand it off to Axtu.
Okay.
Would you like to share a screen or?
Yeah, I think I'll just share a whiteboard probably.
Sure.
Let me share whiteboard. Okay. Just I go find the problem statements so I can just paste them on. Okay, so this is the first problem. I kind of forgot the name, but it's like about stars. So basically we have wait, can we make it so that only I can edit? How do I do that again on whiteboard? Whatever, it's fine. Just no one else, please write, please. Yeah, can no one else write? That'd be great. Okay, so first problem, I'll quickly go over the problem statement. I expect most of you guys to have already read it before though, but I'll just quickly summarize it. So we basically have this n by n grid where, and then afterwards we get three numbers, either, actually no, we get n and then two numbers a and b. So the n is the n by n grid, and then the grid consists of letters of three types, either W, B, or G. So W basically represents I guess instead of W, B, and G, let's represent them as like 0, 1, and 2, right? So let's for the sample, we got W as 0. So there's like 0 stars counted there. B is like 2 stars counted there. And G is 1 star counted there. And the problem is basically saying, so we have the original n by n image, and then the image is shifted by A comma B. So I think A vertically, no, A to the right, B down. And then, so the stars are either shifted or they disappear in the second image. And then this, like the grid we get is the overlap. And we want to find the minimum number of stars that existed before shifting. So for a problem like this, first off, we see that you have to understand the problem statement. This problem statement is kind of complicated, but once you fully understand the problem statement, then you can begin thinking about solutions. So another important thing to do for problems is let's look at the scoring. So the scoring, so we have for first sample case, just the first two cases are just samples. And in the next case has A equals B equals 0. So this is evidently pretty easy. This is just, if nothing moves, then everything that's either gray or black has to be part of the original image, right? And there's no other options we can do. So this is pretty straightforward. Second input, A equals 1, B less than 0. Honestly, I'm not going to cover the second two inputs. The second two inputs are just like casework. So you can try caseworking them. I'm just gonna go into more of the original solution. Well, how do I make it so no one else can edit, by the way? Is there any way? Okay. Yeah. I guess I'll just continue on. Yeah, if everyone can just not write, but that'd be great. But yeah. Okay. So for this, so continuing on, so basically we have these, so we have this condition. So if we like when we see this problem, if we try to cover all the cases at once, it gets really tricky, right? Because the issue is like, for each spot, we don't know if like this was originally there or if it like moved. Yeah, okay. Yeah, can someone figure out how to stop other people from editing the whiteboard? Just figure that out. Is there any way? Um. Sure. I'll just continue. So tackling all at once is pretty hard. So let's try to, because like, every single space can either be like, part of the original image, or it might have been shifted over. So, it's pretty hard to figure this out, like whether it came from originally or from another one. So let's like try to figure out first like what is constant, right? And like what we can guarantee, right? Because like for a lot of these ones, we can't guarantee anything. But one thing we can guarantee is that anything that's like 2 or like black in the original, or I guess like B, right? Anything that has like value 2 must have an original must have an original image in it, and everything that's 0 must not have an original image. Right. So these two are pretty guaranteed. So let's just handle these two cases. So white is pretty easy. So like 0, right? So no original there. That's pretty straightforward. 2 is must have original. So for now, let's just ignore all the ones because the ones make it too complicated. Can people stop erasing the whiteboard? Okay.
Can you click on more?
Wait, what? More?
Click on more and
Oh
then
yeah.
disable participant annotation.
Where do I do that?
Like there's a little bar and you
Is it the one on the bottom right?
yeah.
I don't have that option.
Do you see your screen sharing, right?
Yes.
And do you see it annotate?
Annotate?
And there's a more right next to it. Like
No, I don't
try
think so.
try share again.
Try sharing again. Okay.
Yeah.
Um, I don't see the option.
Um just can you exit the whiteboard now?
Exit the whiteboard. Okay. Let's just stop sharing.
Yeah.
Okay.
And then share again. Share
Okay.
whiteboard again.
Share whiteboard. Let's make a new whiteboard.
Yeah. Do you see the little bar now?
The top left or bottom right?
It's probably top or bottom, yeah.
Um,
Like the bar you can like unmute yourself.
oh yeah,
Do you
yeah.
see
I
the
see that
bar?
one.
Yeah, there's a more. Do you see
Yeah.
more?
Yep.
And disable participants and annotation.
Uh, I don't have that button. Might be some. This would be some code. Wait, if you press that button, will it work? I think it might work if you just do it as well. I don't know. I don't see the. I just don't think that's an option for me. Yeah, like I don't know. Like if I take a screenshot of more, it just looks like this.
I just give you a host. Can you?
Okay.
No, not there. Like, there's a little bar. Like you know where you unmute and you can stop your video.
Yeah, I mean, like
And
this.
there's the security. Yeah. Do you not
Oh, it's in
see
host
the
tools.
option?
Oh, wait. I actually don't see it. Wait, like I hit the more on this bar. Like, okay. I mean, just try continue share. Okay. So if we have like, so we decided that if we have, so let's tackle the black ones first, right? So if we try to tackle the black ones, so let's relevel. So 0 0 2 2 2 1 1 1. Let's just try to tackle the ones that are black first. So the ones that are 2, we know for sure that the ones in this space must have be originally part of the original, right? So let's just create a new array. So a new array, like that's going to store which elements in certain spots must be part of the original, like must be part of the original image. So twos must be part of original. So let's mark this. So for now, the new array for the sample test case now looks like this, right? So we know that these three must be part of the original ones. And then next, let's try. We also know that the ones that are two must also have an original one. Like if we unshift the two, right? So I guess this sample isn't the best for this. Let me go to the let me go to the sample that's let's go to the sample that in the bottom. So this one, right? So if this is 1 1, this would be 1 1 2 1 1 0 0 0 0. Okay, so the new array is so far 0 0 1 0 for everything else. So we know the ones that are two must also have, like, if it's unshifted, must have a one that's in the original array to that part, right? At that spot. So for this one, right? So we know that this is where the two occurred. So at position, I guess let's call it 0 2. So if we unshift this, we know that this spot must have come from 0 1. Start sharing your screen, access the more option, appears while sharing. This is yeah, I don't know. Okay, so this 0 1 2 must have came from 0 1, right? Because if we unshift it, it must have come from 1 to the left. So we unshifted it, and now it must come from 0 1, and that means that this grid, this spot, must have also been part of the original image, right? So we can mark this as true. And this leads us to the second case where basically we see that this is the only case where we might have a -1 appear, where basically if this spot isn't actually gray or white or is like outside the array, we know that this must be impossible because there's no way that a spot could be projected onto this this two spot, right? So for example, if the unshift came from let's say it came from like 0 -1 instead, we know that this must be impossible because then there's no way for 0 2 to become white, to become black. I mean, okay. So we do this, and now we unshift everything. We mark everything in the new array to 1. If it's already marked as 1, then we can just leave it as 1. So now after we do this step, we see that the new array has these spots are required to be in the new array. And everything that's we already handled the black case well. So that's the two things we can get from the black case. And now we can handle the gray case. So the gray case, it's basically saying the gray case is pretty straightforward, as in if we already marked it as necessary in the new array, then we obviously don't want to make it part of the then we can just the gray part of it could have just came from the original array, right? So then we don't want to add. So if already marked, don't add to answer. Otherwise, if it's not marked, then that means that we want to see if it could have been a projection as well. So if not marked, so there's two cases. So if it can be a projection of an existing one, right? So let's say that, I don't know, we're at this square and like this square could have been projected from this one. Like I know this isn't the actual sample, but if we just say it is, then we actually don't have to spend another we don't have to make the original this square darken the original one because we could have just projected this marked square onto this one. So that saves us a one from our answer. So if can be projected, don't add, don't mark it. Otherwise, we have no option, right? So, like, if it can't be a projection, that means that it couldn't have only existed in the second array. And then, so that if that's the case, then we have to add it as part of the original array. Make or add to answer. And then the final answer will just be everything we mark in the original from our first step. And then from our first step with the black nodes. And then we see how many extra ones we have to add on top of that for our second step. Does this make sense to everyone? Does anyone have any questions? If anyone has any questions, please speak up because otherwise I'll just continue on to the next problem. Okay. No questions. I guess so the main part about this problem is basically just to split it into multiple cases. Like it's really hard to test everything at once. But if you break them up into like, okay, the ones we know for sure are guaranteed. So like the white and black ones. White, you don't have to do anything. Black, we can do in a pretty easy step. And then lastly, the gray ones are the ones that are complicated. But after we mark the black ones, the problem turns pretty simple. Okay. So let's go on to the next problem then. Let me copy paste over the next problem. The problem statement is pretty short. So we have, I'll quickly summarize the problem statement though. So we basically have this string of, actually not string, so the array of n integers. So the n integers are numbers from 1 to n. This part's actually kind of important, so keep note of this. So Farmer John defines a like this mu in the array as basically 3 numbers where the second number is equal to the third number, but neither the second nor the third number is equal to the first number. And yeah, we just want to count the number of distinct mu's. So let's see for the sample. Here for the sample, like we have 1, 2, 3, 4, 4, and the possible ones 4, 4, 4, and the possible ones are just like 1, 4, 4, 2, 4, 4, 3, 4, 4. And also notice that like even though like there's multiple ways to choose 2 4s, right? We can choose these two, or we can choose these two, or like these two, right? All of them are counted as the same. We just want the number of distinct mu's. So for this answer, it's only 3. Okay, so that's the problem statement. Let's see about how we want to solve this. I can't think of a super good way to get the earlier test cases. Actually, no. Okay, it's to get to n equals like unless it's 10 to the second test case, right? It's pretty straightforward. We can just loop through and select any 3 numbers, any 3 characters, check to see if this if this mu has already been discovered, and then record it, and then continue on. For n less than 10 to the 4th, you might have to do a slightly n less than 10 to the 4th. Does n squared work for n less than 10 to the 4th? I don't really. If n squared works, then you can do like an n squared solution where you loop over the two the basic basically a mu is like a b b, right? It follows this pattern. If for n less than 10 to the 4th, you can loop over like n squared, loop over like the a's, check the a, and then loop over b, because you don't actually need to loop over both of these because we know that these elements are going to be the same. So that's the n squared solution. I think n squared should pass for inputs 5 to 7. Okay, so for the so that's how we can get some samples. So 2 to the 4 is inputs 2 to 4 is pretty straightforward. 5 to 7, I think the solution for 5 to 7 is you loop over A, you loop over B, and then you will for each B you want to see if there's another B behind it. And this actual solution is actually going to be pretty simple, pretty similar to the actual solution, which I'll start going over now. I think this problem there's like probably a lot of ways to do it, but I think the main thing you want to notice is every time we pick a mu, it's basically saying, okay, so if we fix the second number, right? If we fix the second element, we're just saying, okay, does another of this element exist in the future? And then if it does, we can just count how many distinct numbers are before this element. Yeah. So a good way to do it is kind of like a frequency table, but I think a better way to do it is just like count number of distinct elements at every single spot. So let's go for here. So if we take the sample inputs, right, we have a distinct array, that we can maintain. So basically, we want to also store the last occurrence of each element. So last occurrence of each value. There's a lot of ways you can make a distinct array. You can use like a frequency table, or you can just store the last occurrence and just like basically see if an element has occurred before. So the distinct array, like after we make it, is going to end up being 1, 2, 3, 4, and then 4, 4. Right? Continue on. And we can see like this basically is just storing, the first 4 elements are distinct. The next one has occurred before, so that's why we don't update it. We keep it at 4. And the way we set it is basically, yeah. So every single time we go to the next element, we see if the next element has never occurred before, we add 1 to the previous one. Otherwise, we just keep it as the previous one. Okay. So we have this distinct array. Now we just have to see for each element what kind of answer they can get. And basically, like if we have a case, for example, it's like 1, 2, 3, 4, 4, 5, 4, 4. We need to make sure that we count all 4 cases for the like the moves that end in 4, 4, right? So for this would have an answer of 1, 4, 4, 2, 4, 4, 3, 4, 4, 5, 4, 4, right? So we have to make sure we get all of these cases and not just take the first pair of 4s we see. So the way we do this is we have to make sure we get for each like element that we're going to use as like the B part of our move, right? If our move is like ABB, right? We have to make sure we find the last occurrence of BB. And then check the number of distinct elements before this B. So how do we do this? There's a lot of ways to do this as well. I think the way I ended up doing it was I stored basically the last occurrence for every single value X. So last occurrence of each value. So I have this array. And so what this stores is, as I loop through the array, I store, like, for example, where was the last 1 I saw? Where was the last 2 I saw? What was the last 3 I saw? What was the last 4 I saw? All the way up to n. And this is where the fact that that the integers being from 1 to n is important, because I'm actually able to make this array. Yeah, I'm able to make this array basically because the numbers fall into this short range. So as I loop through it, I also want to store basically the value for each. The value for each array. For each, like I actually I want to say value. So let's call it the answer for each value. So this is just updating, and as I go along, I change it. So we see that like for 1, 2, 3, and 5, this doesn't matter, but let's just like see what happens to 4 as I loop through, right? So when I hit this 4, the last occurrence of 4 was originally -1, but now I update it to let's say update it to 3. Okay. Because this is, so indexes are going from 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 10, right? And then so this, when I hit this 4, I update the last occurrence to 3. When I hit the next 4, I update the I see that it's been visited before because the last index was actually 3. So it's been visited before. And then I can update the answer for it for like the value of 4 with the number of distinct values before it, before this 3. So the number of distinct values before is going to be not counting the current one. So I'm going to update the answer as 4 minus 1 equals 3, right? And then I keep going. I hit the next 4, and then this 4. I can see that the last occurrence was this one because I stored it in this array, right? So I want to update this value. First I want to update the answer. When I update the answer, I see that the number of distinct values before this 4 is still going to be 4 minus 1 equals 3. So the answer doesn't change, but I can update the last occurrence now to 6, right? And then when I hit the last 4, I see that I try to update the answer, and I see that the number of distinct values before this 4 is now going to be 5, and I subtract 1 from it to not count the 4 itself. I get 5 minus 1 equals 4 as my final answer. So there's a lot of ways you can do it. I think you can also probably do it just by storing like where the last occurrence of each value is, and then like for each time you can like update the answer. But the most important thing is that like you're always going to like you have to make sure you do it in one iteration and that you find the last 2 of each element. And like you basically take the answer from the second to last element. Does this kind of make sense to everyone? If anyone has any questions, yeah, please ask in the chat anytime. Okay, so I think that for this problem, the way you want to kind of approach this is, I guess, just by like, I mean, just think about like, so we look at the time, we look at the time limit, and we realize that this problem must be done in O of n time, right? So first we see that like n less than 10 to the 6th, it must be done in O n time. And when we see that, this basically is telling us that we have to do it in like, it doesn't just have to be one iteration, but we can never have a nested for loop, right? So we have to do this with a sequence of just of iterations through the array. So yeah, the first step is like we want to consider like, so how do we do this without looping through the entire array multiple times? And we see that, you know, if we have a pattern of ABB, all we have to do is like if we can fix this value, the values here, all the problem boils down to is counting the number of distinct values before this B, right? Whatever index this B is at. And then, yeah, that's how this problem turns into number of distinct values. I think, am I allowed to share? I should be allowed to share code for this, right? I think this problem is probably better explained by code. XCamp admin, am I allowed to share code for this problem? Wait, yeah. Does or like sure do you know if I'm allowed to like I should be able to share code, right? Because the contest is over.
Yeah, I think it's better to be like something like a pseudocode would be better, but like probably it's not that good to share the full code yet.
Oh, okay. Okay, I won't share the code then. Okay. Yeah, but so there's basically a lot of ways to do it. The main thing you want to do is just like the distinct index. Like you need the distinct array, I'm pretty sure. So distinct array is something necessary. And then yeah, so you just want to find the second to last occurrence of each distinct value. So you definitely also need some kind of array storing where each array was where each array element was accessed. Now think about it, another good way could potentially just be from looping from the back. So you loop from the back, and you just like that's another really easy way of finding the second to last occurrence. So yeah, there's definitely multiple ways of doing it. So like if you loop from the back, right, you find the first 4, so you don't take it. You find the second, you see that 4 has been discovered before, and this is the second 4, and then you can just add the answer for that. So actually, yeah, like now I think about it, this is probably definitely a better way. So after you make the distinct array, just loop from the back, find the second to last occurrence of each element. Does anyone have any questions? Not really? Okay. I think I'm going to continue on to the third problem then. So the third problem is probably the hardest problem of this contest. I think it requires a pretty clever observation. I'll just show this for now. So problem statement, let's explain this first. So basically we have n cows in a line with cow 1 at the front and cow n at the back of the line. There's also n species, and again, the species are going to be numbers from 1 to n, and we're basically just given this array of n numbers, each from 1 to n, And then, but we also get the second array, which basically says, okay, we want to match the numbers. We want to count the number of matches from the second array to the first array, but we're allowed to do some operations to the first array. Namely, we can choose any segment LR such that 1 less than L less than N. So basically just any segment of the original array and reverse all the elements in it. So this, like, if we have like 1, 2, 3, 4, 5, 6, right? If we pick this range, then after reversing it, it becomes 1, 2, 5, 4, 3, 6, right? And the rest of the array remains untouched. And we want to see for each array, we want to find basically, I guess the better way to think about it is after doing, like, if we do every single possible operation, the number of like, what are the possible values, like the possible values we end up getting, right? So basically for, let's take a look at the sample case, right? If we have 1, 3, 2, and then we try to match it with 3, 2, 1, we see that if the segments, there's only six possible ways we can switch. Six possible ranges we can choose. If any of the ranges are size 1, right? So either they basically don't affect the array at all, and that's why there's going to be 3 values that remain 0 because the original array matches 0. So 3 was 0. And then the second array, but then if we choose to switch these two, right, we get 3, 1, 2, 3, 2, 1. This is 1, so that's why we add 1 to this answer count. Next, if we try to swap the second two, we can get 1, 2, 3, 3, 3, 2, 1, and this matches 1 again. So that's another one. We add another 1 to the possible answer count of 1. And then the last one is that we reverse the whole array. We get 2, 3, 1, 3, 2, 1, matches 1 again. So that's why the number of ways to get 1 as the final answer is also 3. Okay. So we clearly see, so we see that there's going to be, actually first, let me first talk about the scoring, So we have basically 3 test cases where n is less than 100, and then the rest of the test cases where n is 7,500. So for n less than 100, we see that we can do an n cube solution, and I hope that everyone can get this problem because this is just going to be there's going to be a total of n squared ranges, right? Because the ranges are just like any L from within like L from 1 to n, and then R from L to n, right? So if we have a nested for loop like this, the time complexity of this is n squared. There's n times n combinations. Technically a bit less, but yeah, it's still in the range of n squared. So if we have n squared values, we can see it's pretty easy to process every single range with O of n time, right? We can just loop over every single possible range and then just reverse this range. We can reverse the range just by looping over it. That's O of n time. And then we do a quick check. So that's another O of n check and then check, right? So I hope everyone can see like this solution, the n less than 100 solution. This solution would be n cubed, but this passes for n less than 100. But we see that for 7,500, n cubed is not going to work. We're going to need an n squared solution. So how do we approach the full solution of this problem is we kind of want to build off this original. The issue, like we can still see like no matter what we do, right? We're going to need to test all n squared ranges. This is something we can't avoid because like there's pretty much no way we can find an answer for a range without like actually checking over the answer for a range. Like if that makes sense to everyone. Like at a certain point, like we're still going to have to see all n squared ranges. And then what this tells us is that like we somehow have to make this part O of 1. So we have to make processing each range really fast. So how do we do this? We see how each range, so like to do this, right? We want to see how each range can build off a previous range. like, oh, this is going to be a common occurrence in a lot of problems, right? Or it's like going to be, especially for ranges, because we see that like if we have a range, right, like from like one, let's say from I to J, if we go from this range to if we add one to the next, like from I to J plus one, almost everything within the range stays the same, right? Like all of these elements completely match up with these elements. These elements are the same. We just added one element at the end. So this is just a really common technique for range problems. We want to see if one range can build off to the next. And let's test for this problem if we can. So if we have a range from I to J, and we want to instead see the range from I to J plus one, we see that there's a bit of an issue, right? So let's just say, like, let's just call the original range is now going to be from I, like I plus one, I plus two, dot, 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 J, right? And once we reverse it, it's now J, J minus one, J minus two, dot, 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 I, right? But if we have from I to J plus one, I plus one, dot, 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 J, and then J plus one here. Once we reverse it, we get J plus one, J, J minus one, and then dot, 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 all the way back down to I. But we see that the issue here is that like this isn't nothing here, nothing in these two arrays is perfectly matching, right? Like everything is like shifted by one off. Like this I and J should be matching. This I and J, like everything's one off because J plus one is now where J is supposed to be. So this doesn't actually exactly work. But if we continue on this, like if we look at it more carefully, we realize like if it's only one off, what's a way we can make it not be one off, right? Like that's going to be the main thing. And we recognize that the way we do this is by instead of going from I to J plus one and trying to reverse that, what if we go from I minus one? Why is my pencil super? Oh, that's highlighter. We try to go from I minus one to J plus one. And let's see what happens to our new array when we do this. So now we have I minus one before this, then I plus one, dot, 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 J plus one, right? And we can kind of like imagine like the imaginary indexes like this. I know I'm kind of messy, but like there's like kind of indexes, right? So like these elements are on the same index. So once you flip this array around, what we get is J plus one, J minus one, dot, 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 and then I plus I minus one. Right. And this matches up really well with this, does it not? Right. We see how every single element within these two arrays are now matching, except for in the original array, right? We had J minus we had like I minus one before it because I minus one remained unchanged and J plus one after, right? While in this array we have these two elements swapped. But now this is like a really easy, like not I won't say easy, but like now like this we see like a clear transition here basically. So we have an original array. If we add one to both sides and then reverse it, it's going to be the same as the original range reversed, except these two elements are swapped now. So this clears us a very good way to go from one range to the next. If we add, like we see that the answer, so if we have an answer for this range, right? Answer for this one. The answer for this one, I guess I'll call this like A1, like ans1. Okay. So answer for this range. Ans2 is now going to be equal to ans1. But then we see like what the contribution from swapping these two elements is, plus contribution for swapping these two elements from swapping endpoints. And this could be negative or positive, right? So if like these two originally were matching, but then now we swapped them and made them unmatched, we subtract 2. If these two weren't matching before and now we swap them and now both are matching, we add 2. If one was matching, one wasn't matching, like whatever. It's casework, right? This is pretty straightforward. There's not that many cases. There's like 4 cases total. yeah, you can just write this as casework. But either way, like the more important thing is that we can calculate this in O of 1, like basically a constant time, because there's only 4 cases. We just loop through all 4 of these cases, or like not loop through, just check through all 4 of these cases, like 4 different if statements, and then we get this value, and then from this way, right, we can get the answer for this new range in constant time, which is exactly what we're looking for. Does this part make sense to everyone? I think this part is like the most important part of the problem. Oh, wait. Okay. If no one has any issues with this part, then I'll go on to like more specific implementation details. So how we want to implement this then is basically by starting with elements of the smallest amount and then slowly increasing them up, right? Because we see how like every single range builds from a range of like that's too small than it. But the other thing important thing we have to look out for is we have to make sure we don't count a range more than once. Okay, so how we implement this then is if we have this original array, let's say, I don't know, I'll use the second example because it's longer. 2, 2, 1, 3, 2. We take this original array. We just want to start, we in order to not have overlaps, overcounting, we basically choose where the center is going to be. And if we pick, so every single range we know is going to have like a different center from another range if it has a different length, right? So like even if two things are the same length, this one has center like here, this one has center here, right? So we basically just want to loop through the center on the outer loop. So like for center from 1 to n. And the other important thing is there's 2 different types of ranges, even and odd, and this is just some case we're gonna have to do. So let's tackle the evens. Let's tackle the even ones first, right? So for even centers, we loop the centers from like, these are the possible even centers. And then from each of these centers, we try to grow the range by adding 1 to the left side, 1 to the right side each time until we're not allowed to do this anymore. So like we loop, so like for, I guess like, length from 1 to n on the outside as well. And then if it ever goes outside, we just stop doing this loop. And otherwise we update the value for range. And we do this both based off the previous value we calculated for this center. So we like create a value here. Oh, the important thing is like the value for each is like the value for the original array. So value for equals original array. And then we can, loop the length, update the value for the range, and then process this both for even and odd. So that's another thing you're about to worry about because so we process the one that runs to the center in between values, that's even. But then we also process the ones where the centers are on the elements themselves, right? So this, right? Because this creates ranges like here, of length 3. This one creates a range of length 3, then create a range of length 5. Yeah, so on. Anyone have any issues with this? Okay. If not, then if there's no questions, then I guess I'll go over just a bit of contest summary. So, let me pull up the slides. Where are the slides for the, okay. Okay, so this is the slides. Let's see. Yeah, so overall, I think this contest was a lot harder than the previous contest. I'm anticipating the cutoff to be around 650, if I had to guess. I think this contest was, I think this contest was actually pretty hard. The problems I think were solvable. Probably like A is kind of solvable. Like if you make the observation, B is like also a little solvable. So A is like I'd classify it as like ad hoc / greedy because it kind of requires you just to make the observation that like we can greedily process the white ones first, the white and black ones first, and then process the gray ones after. So you just had to kind of count with that observation. For second problem, B is just yeah, you just have to be able to. It's just ad hocs. You just have to be able to like make the observation that you want to count the number of distinct elements basically for each element. And for number three, yeah, number three was definitely the hardest one. So number three, you also needed you needed like experience of range queries like this. So I think it's definitely a really important skill to learn, and it's like it's really hard to like come up with in contest if you've never seen it before. But yeah, so I mean, I think I think the cutoff's gonna be really low, but I think for number three, you could have at least gotten the first 6 test cases. Number two, I think you could have gotten the first the first sample. No, I mean, the first set of test cases was pretty easy for number two, and the first set of test cases was also really easy for number one. So for the people who like only got like who didn't get like any points on a problem, definitely in future contests try to look for the smaller test cases and try to solve those for sure. Yeah, but other than that, I think there's not much else you can do besides just practicing a lot more problems. Like I think bronze these days is moving just it's always just ad hoc / greedy. You just always have to be able to make these observations. And the only ways to improve on that is by solving more problems and getting more practice. I think that's pretty much all I have to say. I think I'll turn it back to Xuan Laoshi now. Thank you for listening, everyone.
Yeah, thanks, Alex. And yeah, thanks everyone for attending the Bronze live solution session. And we will start our silver solution section in 8 minutes. And for now, if you have any questions, feel free to post in the chat. And also, like either technical or non-technical is all fine. Or maybe you want to pass bronze, but somehow you got stuck. Those questions are welcome too. So if not, then we will probably just pause here and then wait for the silver session to start. And by then, we will just, I'll stay in the Zoom link and wait for everyone to pose any questions. And also, very importantly, as lecturer Alex mentioned, for Brown's question is never that difficult at all, but instead it's more like you need to gain a sense of competition in the sense that you want to do some more mock tests and also at least practice some set of problems to gain enough muscle memory so that the problems, the context is not less stressful to you. And also merely doing the homework, even if you are at XCAM, is still not enough. You have to really get more practice. You can either work on the past USACO contest problems, and you can also choose to attend XCamp mock test class. But essentially, it's pretty similar, but probably the mock test class is closer to the real USACO contest difficulty based on lectures assessment. And another thing that we would highly recommend you is that typically if you practice at home on a week-by-week basis, typically you have a lot of things together. You probably won't get the whole chunk of time to work on USACO, which is kind of required for you to pass and also gain enough practice, especially in silver and above. So camp format would be really highly recommended. And I would not recommend you to attend any camp virtually. Instead, try to attend the camp offline, like just talk to the lecturer and work with the lecturer face to face for a week or so. It'll gain much more than you can imagine. I've seen so many students got the momentum from the camp already. Okay, that's all from me for now. We will pause here and I will share my slides and wait for the next one to start.